So what we have seen so far is that we can do some kind of basic operations with MIPS, addition, subtraction, and I showed you kind of the format of what an instruction would look like. I'm going to kind of get to this point um, where we stopped here, where I wanted to introduce registers, and that's going to require that we do a demonstration, I think, to get more of an intuitive feel for it. Switching over to Mars, and I think you should be able to, yeah, so you should be able to see this. So the layout of MIPS assembly instructions, I changed this slightly so to show that everything that has a pound sign or a hashtag represents a comment. So all of this is a comment, and then everything in red here is a comment, everything to the right of that pound sign, the hashtag. So if you have elements that you wish to put in memory, you're going to use this space, a so-called dot, D-A-T-A. So it's a directive. Anything with a dot is a directive. And what you're doing is directing the assembler to say, well, what comes next? Place into this particular area or format it or put it in a certain way. So this places everything that comes after the dot data into a particular address. So it's the 1001 1000. So I think, let's see, 1, 2, 3, 4, 5, 6, 7, and then I think there's one more zero after that. So it's a 32-bit address. And I know that when I'm looking at this in hex, each one of these hex values require 4 bits to represent the numbers. So each one of those hex values would require 4 bits. So this right here, this 32-bit value, 1, 2, 3, 4, 5, 6, 7, 8, I know that then would be my 32-bit value. Or could be represented by a 32-bit value. Also, for this executable code, he exists in a very specific area. This is the actual running of your program. So there's an addition here where our discussion last time, let's see if I can annotate on this a little bit. So when you have something like this, what it does for you is this is really shorthand for T1 equals T2 plus T3. So thankfully, that layout where you have what's being assigned a value to the left and the two operands are over here to the right. There are certainly other languages that might have the guy that's being clobbered off to the right, do an addition with 2 values and store it. So this makes it a little bit easier to understand what's going on with the assembly, generally with MIPS assembly. It follows a familiar pattern. So explaining the instruction in that way, that part makes sense. Hopefully that's pretty easy. What takes a few more minutes, I think, to talk about is the fact that these are registers. For 90% of us, the idea of a register is a foreign concept. So I want to spend a few minutes talking about what a register is. Storing values, let's go ahead and, let's continue sharing this. Storing values in memory is different, right? Just laying things out in memory is different than putting things into registers. Registers are hardware, and they're very, very fast. Hundreds of times faster. If you want to access something from a register and extract the data, it's much, much faster than accessing information from memory. So when we do this with the .data segment in that directive, we're just putting things into memory so that we can get out later. But but everything that happens in the way of addition, the hardware is using those register values to do the addition, subtraction. Like you have to pull information into registers, into the hardware, so before you can actually do anything with it. So what is a register? That's the important conversation today, just to spend a few minutes thinking about what a register is. Off to the right, there are these 32, 0 through 31, 32 registers that we have. And then you'll also see PC, HI, and LO. Those are also registers, but those aren't registers that we can write to or store values in any traditional way. These are populated as the result of an operation. So we don't have as much control. I'll show you what that looks like a little bit later. The 0 is a register that just will always have a 0 in it. Lots of times we will need a 0, and it's convenient to have a 0, a register that's always guaranteed to be 0. So let's jump over to this PowerPoint, and let's see if this can work so that I can write on it. So a register, one of the core and most important components of a register is what we call a flip-flop. So a flip-flop is a circuit that can hold a certain state. So it can hold a bit or a voltage, either high or low. So ultimately, this ends up being like a 1-bit memory element. It's a single bit memory element. Well, at least it's a component of it. You'll see how we build this up. And if we can store a single bit and hold it there, then we have memory. So our registers that we look at over the next few minutes can also be pulled together and have been used. I can show you a particular Texas Instrument component that uses these ideas and they sell a memory to build a memory product similar to your RAM, but you can build memory using flip-flops. So what I'm going to do is use a Q. I'm going to use the letter Q to indicate output. And if I can, I'm going to try this share again and hopefully be able to write on it. Let's go for it. Yep. So can you see, what do you see right now on your screen? Do you see something that says basic logic gates? Yes, good. So here's been one of the interesting challenges in the last couple of days. I just learned that the newer version of Java has problems with what I'm showing you here. So this package here is Logisim. And Logisim was used, well, is what we typically use to simulate logic operations, AND gates, OR gates, exclusive OR, and when you can put these AND gates, OR gates together to build a computer, to build a CPU, to build something that can do addition, and to build a register in our case. So the more common way of representing an AND gate, the more common way of representing an AND gate is to use this type of diagram or schematic diagram. And this is the more common OR. And then this one here is the NOT gate or the inversion. So these are, if you look at the AND gate, if I have two voltages or two inputs going into them, I have 0, 0. I only have 4 different combinations that I can bring into this OR gate, X and Y. So if I bring in a 0, 0, for all of these, there's a script, I suppose, that's often helpful. With the AND gate, the script is the output will be true if both inputs are true. And that's the only time. So the output for the AND gate will be true, and I'll use an X and it. Since I'm running out of space here, I'll just use a dot, kind of a multiplication symbol, X and Y. So the output will be true only if both are true. So it is the logic of AND that you should have seen in Math 130 or the program, the introduction to programming prior to this class. We can do AND gates, we implement AND gates with hardware. The OR gate should have familiar logic to you as well. For the OR gate, I'm going to use this symbol here. It's common to use what looks like a plus sign for OR, and 0, 0, 0, 1, 1, 0, 1, 1. What are all of the combinations for this truth table? Well, so the kind of the script for the OR gate is that the output will be true if either one of those is true. So it won't be true here, and it says it's an OR gate. So it says, is either X or Y true? Question mark. And the answer is yes. One of them is true. One of them is true. At least one of them is true. So that's the output that we're expecting for the OR gate. A little bit later, we'll see another OR gate that looks like this. So the standard OR gate diagram, but it has this extra kind of bar here. And then this one is exclusive OR. So let me just put an XOR. So this is the exclusive OR. And what it says is that given X and a Y and the same combinations, the output will be true if only, so I'll do an OR, but I'll put a circle around it. That's a common. That's one way of showing an exclusive OR. So exclusively one of them. So this looks largely like the OR gate, except for the one output here. So it means that exclusively one of the inputs is a 1. So whereas the OR gate just says, do we have at least one of those showing up as a 1? And then finally, the inversion is only a single input. So I don't need an X and a Y. So it has an input and then it has a particular output. And so whatever I put in there, the output will end up being the opposite. So if I put in a 1, I get a 0, and then it's going to be hard to see. And if I put in a 0, so a 0 gives me a 1 gives me a 0. So it just negates. A 0 becomes a 1, and a 1 becomes a 0. So those are the fundamental gates. Using these 3, those bottom 3, the AND, the OR, and the inversion, you can build memory. You can build registers. So these I'm used to kind of working with for the last 10 years. What happened recently is that when I update it, and possibly when you've updated, when you update your version of Java, Logisim has not been, the original Logisim, the one that's even posted on our shared drive, hasn't been updated probably in 11 years. So there are other institutions that are doing branches of Logisim, and they want to extend it. So there are thousands of students and hundreds of, or at least many institutions that are still using Logisim because I think it's a wonderful teaching tool. And I've heard a number of students say, you know what, Logisim is actually really easy, and I've been able to take this into, when I've transferred over to San Diego State or elsewhere. So it is a useful tool, and I know that some will get great benefit out of it. The challenge is that it's, one of the things with this new version of Logisim, the one that I'm looking at now is Logisim Evolution, is that instead of these gates, now it's using these gates over here where it's a simple box with an and sign. So the ampersand is what it actually is. This ampersand sign, the and sign, is equivalent to what we see off to the right with the and. The or sign, I think, is interesting. It's rare to see this, but there's this greater than or equal to 1. At least for me, I'm not used to seeing the or represented with a greater than or equal to 1. So one way of thinking about this or is that this output will be a 1 here if the sum of those two inputs is greater than or equal to 1. And then the inversion down here operates in the standard inversion. Now, what can you do with this information? So before I do anything else, just to say a quick couple of words more. I think there was a question about the exclusive OR. The exclusive OR, don't forget, whenever you have two inputs, I'll just write this again to answer a question that came up in the chat box. If I go through this and I have two inputs, if I'm going to take those two inputs and perform a so-called exclusive OR operation, what I'm asking myself in the sentence I suppose that I would write with an exclusive OR, the question is it true that only one of these is a 1? And the answer here would be a no. And you'll answer a no with a 0. You'll answer a yes with the 1 or a true with the 1. So this is a so-called exclusive OR. Is it true that exclusively one of these is a 1? Sure. Is it true that exclusively one of these guys is a 1? The answer is yes. Is it true that exclusively one of these is a 1? The answer is no. So an exclusive OR means that there's only a single one of the two and not both of them. So an exclusive OR says exclusively one of those two bits is a 1. A regular OR says, do I have a 1 anywhere? And as long as you have a 1 in there, he's true. So that's the big difference. And so they really differ in that last, let's see if I can highlight this. They really differ in that last column or the last row. So that's the big difference between those two.